section 8.10, and our objective is that I can represent addition, subtraction, and multiplication of complex numbers on a complex plane. So we're going to be working with vectors and being able to draw those today. But really quick, let's look at our warm-up. And number 1 wants us the directions to write the following in polar form. So this is what we practiced yesterday or in last video. If we have a number of the form -3i, we have to remember that that real piece would be 0 in this case, and the imaginary would be -3. So to write it in polar form, we need to know the length of the modulus or the radius as we're thinking of that rotation. So we're going to definitely be using that Pythagorean theorem of those real values and imaginary values squared and added together. So 0 is nice, but then we have -3 squared, which is 9, and the square root of 9 is 3. And then we have to find our theta by taking the inverse tangent of our b over our a, which anything over 0 is going to be undefined. So if I'm using my table for tangent, anything that's undefined would be at 90 degrees or at 270. So we have to make a decision. Do we want the 90 or do we want the 270? So when I think about graphing this, if I was plotting this on a graph, it doesn't go left or right on that real axis, but it does go down to that -3. So I do want the 270. I don't want the 90. I want that negative axis this time. So I now have enough information to write my polar form. I take my modulus times the cosine of 270 plus I sine of 270. So here is our complex number in polar form. Number 2 wants us to go backwards and to write this in rectangular form. So here we have a complex number written in polar form. We see our modulus, that radius is 3, and we've rotated 270 degrees. So what would be its coordinates in rectangular form? So we know that this first piece is representing our real and the second is our imaginary. So if I want to find my real piece, I need to take my radius times whatever the cosine of 270 is. So again, I maybe go back to my table and I'm looking for the cosine of 270. So my 270 column meets my cosine row at 0. Cosine of 270 is 0, which means my real value is 0. And my imaginary, so again, we still have our radius, but times the sine of 270. So again, 270 column, but the sine of 270 would be a -1. So our imaginary value is that -3. So as a rectangular coordinates here, real, comma, imaginary. So there is our complex number as in rectangular form. So let's go ahead and look down below. We've got a couple of graphs to look at here. Today we're going to be representing complex numbers on the complex plane, but we're going to be looking at their operations, so addition, subtraction, or multiplication. So we're going to start with addition and subtraction. In this first column here, we have a complex number and its conjugate. So remember, if we're starting at the origin, we go over a real distance and up that imaginary distance of b, and we also have conjugates, which would go the same real distance, but they go the opposite imaginary distance. So anytime we have a conjugate, it just should be a reflection across that x-axis, because all that's changing in a conjugate is that imaginary piece. When we go to adding and subtracting, then we're going to actually bring in some information that we learned last year. So hopefully this feels a little comfortable from our vectors unit last year. But let's start with adding complex numbers. So let's go ahead and read down below the graph first. So it says, adding complex numbers can be demonstrated geometrically by showing the addition of the vector associated with each complex number z. So we've seen that z lots before. So here we have the sum of -3 plus 2i and 1 plus 3i. So let's remind ourselves in vector addition how we would do this. So our vector would start in component form, so at that origin, and we're going to go to -3 and then +2. So on my real axis to -3 and then up to +2. So here's where my vector ends. But then I'm going to add to that 1, 3. So 1 is a real axis. So we want to go to the right of our current location because we'd like to have a +1. And then we're going to go up 3. So we started at the origin, we went to -3, 2, and now we've gone 1, 3. And this is where we end. So our resultant, that answer to this, goes from the origin directly to this final destination, that -2, and there would be a +5. So right below there, it says, I'll highlight here, so the resultant is this vector, which can also be written as the imaginary complex number, a complex number. So when we add two imaginary or two complex numbers together, it's just like adding vectors. We're going from location of a tail to a tip, and from that tip to another tip. So adding is just going to increase, and that resultant, we want to go from where we would initially have started to where we ended. Subtraction is very similar, except subtraction we have to do the opposite of. So right below the graph, it says that subtracting complex numbers can be demonstrated geometrically by showing the subtraction of the vector associated with each complex number. So we can again show this subtraction of complex numbers using vectors. So we're going to start with the same complex number, -3 plus 2i. So from our origin, over 3 and up to 2i. So here we're ending, but then we'd like to subtract. Now remember, subtract means to do the opposite. So I would like to do the opposite of 1 plus 3i. Well, the opposite of 1 on the real axis would go to the left. So instead of going to the right, I'm going to go to the left. It's the opposite. And then to go the opposite of 3, instead of going up, I would go down. 1, 2, 3. So the opposite goes in the opposite direction. Left 1, and then we went down 3. So again, our resultant would go from the origin to that final point. And again, I'm going to highlight, this would end up being that resultant vector of -4, -1, which is the complex number -4 plus, or excuse me, -4 minus I. So when we're adding, we just go from a tip and then we continue on our tail. But if we're subtracting from that tip, we want to go in the opposite direction to get to our new tip. Let's try one on our own. Example 1, we would like to add these two together and represent their sum graphically. Now we can do this in any order. We could graph it first or we could add it first. So we already know how to add complex numbers. We know we need to take the real components, 5 plus, and this should be a -2i, so if yours doesn't say negative, will you change that? So we'd have 5 plus -2, so that would be 3. And then we do a similar thing with our imaginary pieces, -2i plus a +4i. So that would give us 2i. So here we have added our two complex numbers together, but let's show those graphically represented with vectors. So my first complex number is going to go first. I'm going to start at the origin and represent the vector that would be 5, -2. So I'm going to go to 5 and then -2. Because this is not my answer, I'm going to go ahead and make this a dashed vector. I've started the origin and now I'm currently at 5, -2. And now I'd like to increase this by a -2 plus 4i. So I'm going to, instead of going to the right 2, I'm going to go to the left 2 and then up 1, 2, 3, 4. And again, I'm not going to draw a solid vector because I'm not finished yet. So we started the origin, we went to 5, -2, and then we went a -2, +4 distance. My resultant should just go from that original beginning point to my ending point. So my tip should be pointing at 3, 2. Let's go ahead and turn it to the back side. All right, for example 2, we're going to do some subtraction. So just like addition, we can take and subtract the real components and the imaginary components. So I'm going to take -4 minus 2, so that would be a -6. And be careful here because -2i minus a -3i, well, that would end up to be really adding 3i. So that would give us a positive I. So let's go ahead and show this graphically. How can we use vectors to show this subtraction? So again, we're going to start at the origin. We're going to go first to the vector -4, -2. Again, I'm going to draw with dashed line there, or dashed vector. So from this point, I need to subtract. So remember, subtracting is doing the opposite. So I'm going to go the opposite of 2. The opposite of 2 would be left 2. And then I need to do the opposite of a -3. So the opposite would be plus. So 1, 2, 3 up. So barely fits on the edge of that graph. So from that tip, we've now gone another vector direction, and now we're at -6, 1. So our final resultant goes from that origin to -6, 1. So adding and subtracting, we actually did a little bit of that last year with vectors. So hopefully this is feeling a little bit comfortable. Okay, multiplication. If we're multiplying complex numbers, which we know how to multiply complex numbers, but on a graph, multiplication of complex numbers is geometrically represented by adding the angles and multiplying the moduli of the two vectors. So if we look at the picture of this graph here, we have a vector starting at the origin going to 2, 1. And we have a vector starting at the origin going to 1, 3. So according to this definition, I should be able to take those two vectors and add their angles. So you notice for this first vector, we've got a θ1, so we should be able to find that angle. And then for our second vector, we have a θ2. So if I were to find both thetas, I would add those together to get my new multiplication rotation. So whatever those two added together gives me my final rotation, which they've drawn in here, but we don't know that exact angle yet. And to find their modulus, their multiplication piece, I would take the modulus of each of these smaller vectors, and I multiply them together, and I would get this final one. So we can do by hand the multiplication, and we can see where these vectors add together. So let's go ahead and try one ourselves. So we'd like to multiply 2 plus 3i and then 1 plus 4i. So let's kind of look at their component pieces for a second. So what if we did like the definition above and we found each of their magnitudes and each of their thetas. So let's start with the 2, 3. So 2, 3 is a small vector. And then we'll do 1, 4. So these two vectors we would like to multiply together. So let's find each of their magnitudes separately. So I'm going to start with 2 plus 3i. So to find our magnitude, I'll use z. You could use r if you wanted to. I'm thinking the square root of 2 squared plus 3 squared. And I'm going to go ahead and just do the square root version of this. So we'd have 4 and 9, so that's just going to give us a square root of 13. So I won't figure out the decimal right now. And then let's do the modulus for our second complex number. So we'd end up with 1 squared plus 4 squared, so that would be 16 plus 1. So the square root is 17. Again, I'll leave it like that. So you know the length of each of their moduli, so let's go ahead and find their theta. So we take the second tangent, that inverse tangent, of their b over their a. So I'd probably use my calculator just to make that a little faster. Second tangent of 3 divided by 2. Oh, whoops, this may be in a wrong mode. Let me check that. Yep, that is not in degrees. Let's try that again. Let's see, inverse tangent of 3 divided by 2. There we go, 56 degrees. Let's keep rounding to that nearest whole degree. Similar thing for our second one. Let's see, inverse tangent of our B over our A, which we could just call 4 if we wanted to. So second tangent of 4. So we'll make sure that 9 rounds this up and call that 76. So if I wanted to find out the total length of the product of this vector, I just would have to take, well, let's do our angles first. So for our angles, it says we just have to add them together. So I would take my 56 and my 76 and add them together. So let's see, 56 and 76, 6 plus 6 is 12, so 132. So let's think about this for a second. If my first vector was rotated 56 degrees, that kind of makes sense there. My second one was about 76 degrees, so together we have a 132 degree rotation when we multiply these together, which is going to take us into that second quadrant. Well, what would be the magnitude? So the magnitude is just going to be that product of the moduli, or of those two moduli. So for us, we have the square root of 13 that would need to be multiplied to the square root of 17. And on this one, I would probably use a decimal approximation because now we're towards the end here. So let's see, the square root of 13 times the square root of 17. So about 14.9, we'll call that, round that up to the 10th. So we know about the length of our modulus. So where is our actual complex number located? So if I take my 2 plus 3i times my 1 plus 4i, I should get that ending location. So 2 times 2 as we distribute, 2 times 4i, 3i times 1, and 3i times 4i. Remember, I squared is equal to -1, so that's kind of important as we're simplifying. So really I have a -12 down here that needs to be added to the constant 2. So that would end up to give us a -10. And then we can combine our i's. 8 plus 3 would be 11i. So here's where our final vector should end up. So again, from our origin, we're going to go to -10, 11. So our vector starts at the origin, and we know its magnitude, and we also know how far it should be rotated. So I'm not really shocked that my answer is that, because I already knew my angle of rotation and that my modulus was going to be pretty long. So go ahead and self-assess, and good luck on your assignment.